In this video, we work a couple more problems from section 5.5. These really don't involve any calculus. They just involve our compound interest formulas, but they do help us to understand exponential functions and their applications a little bit better. So we'll still work the problems. And since they're relatively simple and straightforward, we'll just look at the graphs and then discuss them in this video. So this is exercise 97 from section 5.5, which is about exponential functions and their applications. It says, assume you can earn 6% on an investment compounded daily. Which of the following options would yield the greatest balance after 8 years? So our account balance as a function of time, where time is measured, or time is given by t in years, is going to be that principal, that amount that you initially invest, times 1 plus the interest rate. In this case, we're told that our interest rate is 6%. So we type that as 0.06, divided by the number of times that we're compounding interest every year. And since we're compounding daily, there are 365 days in a year. So we'll have a 365 in the denominator. So the account balance is P times that 1 plus the interest rate divided by the number of times we're compounding per year, all raised to the number of times we're compounding, which is 365 times t. And so that's our function a of t. We are generally interested in this for t greater than or equal to 0. So we'll type that in as well. And that is our balance. Now, if we start with a $20,000 investment right now, then we get one balance after 8 years. So it says, which of the following options would yield the greatest balance after 8 years? And then the first option for A is $20,000 now. So what that means to me, and it's a little bit open to interpretation, is that our investment is $20,000, and we want to know, like, how much would the balance be 8 years from now if we're earning 6% on that $20,000, and that 6% is being compounded every day. So I type P equals 20,000, and then we have already entered the interest rate 6%, and that N equals 365 for compounding the interest daily. So if we want to know what that balance would be after 8 years, we just evaluate this function a of t at t equals 8. So we plot that point, we'll label it, and it looks like our balance would be $32,320.21 8 years from now if we deposited $20,000 right now. Again, I'm not 100% sure that that's what the authors intended by that amount, but that's the way I interpreted it. So given my interpretation, we would have $32,000 approximately 8 years from now if we invested that $20,000 immediately. Part B, we're asked, we're given another option. We're saying we're told that we can invest $30,000 after 8 years. But if we're talking about what our balance would be 8 years from now, and we're talking about depositing $30,000 8 years from now, you wouldn't have any time to earn any interest. So the point that I would plot for that is t equals 8 and $30,000, assuming that we're not earning any interest on it at all. So 8 years from now, you just deposit $30,000, and you still haven't had an opportunity to sort of invest there. So we can see already that between options A and B, option A is better because we have $32,000 8 years from now as opposed to the $30,000. And of course, it's associated with the larger Y value when we graph them. Now in option C, we're told that we could invest $8,000 now and then invest $20,000 after 4 years. So here we have to be careful. The principal actually changes. With the $8,000 that would be invested now, we could invest that at 6% and then leave it in the account for 8 years. So that would give us 8,000 times 1 plus our interest rate divided by 365, raised to 365 times 8. That's the number of times we're compounding that interest for that first $8,000. And then it says $20,000 after 4 years. So then we do exactly the same base, that 1 plus the 6% divided by 365. But it only has 4 years to accumulate interest. So we raise that expression to the 365 times 4. And then here the principal amount is 20,000. So we're leaving that 20,000 alone for 4 years. If we add those two together, we get the balance after 8 years with that option C. And we see that that Y value is larger than the others. And it looks like we'd have $38,352.57 after 8 years, if I'm interpreting that correctly. And then option D says, okay, let's say you've got $9,000 now that you're going to invest at that 6% interest. We want to invest $9,000 4 years from now, and we also want to add $9,000 8 years from now. If we're looking at the account balance 8 years from now, that last $9,000 doesn't have any opportunity to gain any interest. But that first $9,000 has been gaining interest for 8 years. So we just end up adding 3 terms. One for the first $9,000, which is the 9,000 times 1 plus the interest rate divided by 365, all raised to 365 times 8 because we're leaving that $9,000 alone for 8 years. Then got another investment of $9,000 4 years later. So you have 9,000 times 1 plus the interest rate over n, that 365, raised to 365 times 4 because it's only left in there for 4 years. And then that last $9,000 8 years from now, we're just depositing that, and we assume, hopefully, we're going to leave the account alone after that 8 years, and it'll still have opportunities to gain interest. But if we were to just look at that account balance 8 years from now, that 9,000 would just be the 9,000. It wouldn't have any interest added to it. If we add all those numbers together, we get the option for option D, and that leads to $34,985 and 11 cents. And so that's in between our highest option and the option, that first option that we looked at using our exponential function. So it looks like the best option is this green option, which was option C, where we deposit $8,000 now at 6% interest compounded daily. And then we deposit $20,000 4 years from now at 6% interest compounded daily for 4 years, as opposed to the 8 years for the first investment. So that's our best option. Notice we didn't really do any calculus. It was just reading the problem statement and then trying to interpret what the authors meant. I'm actually not a finance person, so if this happens to be incorrect, please let me know. This is my understanding based on the problem statements itself. But to me, with this interpretation, option C is the best option. All right, so that is one problem. Now, problem or exercise 98 is also about compound interest, but it's a much smaller deposit. You're depositing $100 in an account for 20 years at R% interest compounded continuously. So here we're using that formula A, that's the account balance, equals P, that's our principal or initial investment, times E raised to the RT. So we're using that formula again, but P is only 100, T is equal to 20, and then we have R% interest, and R varies from part A to part B to part C. It says use a graphing utility to graph the exponential functions describing the growth of the investment for each of the interest rates. Compare the ending balances for all 3 rates. They say the ending balances. Well, we're interested in what the balance is after 20 years. So we want to know what those function values are at t equals 20. So for part A, we have 3% interest. So we're going to graph 100 times E raised to the 0.03 for that 3% times T. Now, if I, actually, hold on a second. If we just graph, that exponential function 100 times E to the 0.03 times T, we get this green dotted line. It's that green curve. Now we're only interested in that for times T greater than or equal to 0. So that account balance at T years from now would be given by the solid green curve. And we see that when T equals 0, we get A equals 100, which is what we would expect because that was our initial deposit. Now, if we want to know what our balance would be in 20 years at 3% interest compounded continuously, we just evaluate that function at T equals 20. We get $182.21. So we actually earned $82 in interest, and this $100 that we initially deposited is still there. We can plot that point, and we see that that's what that point lies on the curve. Now we can compare that to what we would get at 5% interest. Basically, we do the same thing. We change the R value from 0.03 to 0.05. We see this is the, if we are just looking at the exponential function, it's this orange dotted line. We're only interested in the part where t is greater than or equal to 0. So it's the account balance is actually that orange solid line. And if we want to know our balance after 20 years, we evaluate that function at t equals 20. So we have $271.83. So this time we actually made $171.83 by leaving that $100 in the account alone for 20 years. So we can compare that, and then with R equals 6%, we can do the same thing. Here's the function. Notice it's a little steeper. As we increase the value of R, the slope increases. The slope gets steeper. And then if we want to graph just that part of the function we're interested in, we graph the part for t greater than or equal to 0. So that's the solid part. Evaluate that function at t equals 20 to get the account balance in 20 years with that 6% interest. We have a $332.01. So we actually make $232.01 by leaving that $100 in the account for 20 years. So we see there's not really any calculus here. We say just compare them. Obviously, if it's a higher interest rate and you're earning interest, that's better for you. And that's what we see. That all the curves have basically the same shape. And for each curve, when t equals 0, we start with that $100 deposit. But if our interest rates are higher, then we make more money in 20 years than we would with smaller interest rates. So I think the green one was that 3%? I'm not sure. The purple one is 6%. The orange one is 5%. And then the green one is 3%. So you have 3, 5, and 6%. Obviously, 6% would be better if you're earning interest on that. So this is just, I like this example just because it helps you visualize the exponential functions and see that basically they all have the same shape, but changing that value of R changes the slope, makes them a little bit steeper. So they grow a little bit faster if R is larger.